Good afternoon, my name's Daniel Mitchell and I'm a PhD Research Assistant at the University of Glasgow, and this presentation is being presented at the IEEE International Conference on Electronics, Circuits and Systems at Glasgow, October 24th to the 26th, 2022. My work relates to symbiotic multi-robot fleets and millimeter wave frequency modulated continuous wave FMCW radar, which I'm focusing on today. This work in this presentation relates to ground-based inspection for overhead transmission line sag. Overhead transmission lines are located widely around the world and used to transmit electrical energy across large distances. These lines consist of several electrical cables suspended overhead by pylons. In England and Wales, there are over 90,000 pylons and 7,000 kilometres of high voltage overhead lines to inspect and maintain. Decarbonisation of energy supplies will involve a substantial shift of previously non-electric energy demand onto the electricity network. Upscaling of the energy network represents a challenge on the resilience of the electricity to ensure that there is electricity available to meet demand. Cost-effective maintenance of high-power electrical lines are of critical importance, and the overhead linesmen face several safety concerns during inspection of catenary lines, which include working in remote areas, at height, and facing adverse weather conditions. Extreme weather conditions. The headline on the left speaks for itself here. Pacific Gas and Electric pled guilty in 2018 due to a campfire. Our equipment started that fire. Pacific Gas and Electric repeatedly ignored warnings about its aging power lines and faulty maintenance, and failed to follow state regulations. This killed 85 people and in all destroyed nearly 19,000 buildings. On the right hand side, during winter weather, we can start to see different ice melt removal techniques. Melting of the ice via increased current down overhead line and shorting. What you're seeing now is the ice whacker, which is effective on horror frost, but not necessarily ice. And then previously you see ice rolling via vibrations and contact with the line. And this can be difficult to do. As you can see, 2,000 kilometres squared, that requires attention from this company. And you can gain failures due to two wires touching via the extra weight from the ice, or galloping on the lines, which can be due to the wind, and you've just seen a lot of damage there. So a problem encountered in catenary lines includes the change in the amount of sagging, often resulting in line breaks and loss of energy efficiency. This can be due to climatic and seasonal changes where the cables stretch due to warmer temperatures, shrink due to colder temperatures, or the formation of ice during winter, contributing to a further sag in the line. Often these scenarios occur in remote areas where the climate is more hazardous and severe, resulting in engineers having to travel large distances to inspect overhead lines in difficult areas. So, we have deployed our millimeter wave radar sensor, the Frequency Modulated Continuous Wave, FMCW Radar, for the inspection of overhead lines. What you can see on the left hand side is a setup of the FMCW radar, which consists of a horn antenna, a waveguide, the electronics, and then serial ported to the computer. And for this current setup, we're running a 12 volt buck boost out from the USB from the laptop. Now, the key advantages of the FMCW is that it's low power. In the current setup, we're connected via USB. It requires non-contact. It's also non-destructive. We've deployed this FMCW radar for the inspection of corrosion, on the inspection of wind turbine blades, and now for the inspection of overhead lines. It includes real-time sensing and it's non-invasive. We can also include runtime front-end data analysis. And it's also effective in opaque environments, which include steam, mist, smoke, or fog. On the very bottom of this slide, you'll be able to find more information via this reference here. Baseline measurements and naming convention. The cables were all labelled alongside a labelling convention for the pylons. The location was very flat, which made it an ideal location for an accurate investigation for overhead line sag, as within the second experiment. In achieving an accurate inspection, firstly we utilised a laser rangefinder to obtain the overhead line heights at the base of each pylon. It was difficult to obtain these values along the length of the cables, due to the low surface area of the cables, so the values were obtained for each insulator connected to the cable at the pylon. 3 values were taken using the laser rangefinder, and the average was used for the investigation. Within the table, we can identify that these cables were situated from 14 metres to 104 metres in height from the ground position of the pylon. As you can see in the central oval shape, the overhead lines from pylons 3 and 4 on the right are much higher than the overhead lines from pylons 1 and 2 on the left. This area represents the crossover section. The first proof of concept investigation aims to verify this using the FMCW sensor and is discussed in further detail in the next slide. The method of inspection. The proof of concept investigation consisted of positioning the FMCW radar at the midpoint of the cables, directly underneath the right side, as indicated by the red cables and image on the right here. The aim of the investigation was to identify that the overhead lines from pylons 3 and 4 are at higher heights than from pylons 1 and 2. In the second investigation, the FMCW radar sensor was moved at different 20 metre iterations from 0 metres to 210 metres along the length of the overhead cables. The aim of this investigation was to identify if the overhead line sag could be detected along the length of the catenary line. As you can identify from the image on the right, there was foggy and misty conditions, which the FMCW radar had to overcome. Experiment 1. Proof of concept. The graph on the left displays the converted return signal amplitude received at the FMCW radar using the fast Fourier transform. Each peak within this graph represents a detected overhead transmission line, where the bin number represents the time of flight from the radar to the cable, hence resulting in a distance measurement. For results labelled Test 1, the overhead lines R3, R2, R1 and B1 can be distinguished when compared against the sky baseline recorded. For the results within Test 2, overhead lines O3, O2 and O1 can be detected when compared against the sky baseline. In addition, these results verify that the overhead lines from pylon 3 and 4 are at higher heights than pylon 1 and 2. As we can identify from the graph, line K1 is indistinguishable against the sky baseline. This is probably due to the arms on the pylon for the larger pylons being extended further, meaning that overhead line K1 is out with the field of view from the radar sensor. Experiment 2. Identification of overhead line sag. This graph on the left represents the range from the FMCW radar sensor to the detected overhead cable at each iteration along the length of the overhead cable. The table on the right represents the range of values of each overhead line where the trough of each cable is detected at 120 metres during the investigation, as we can see here. What we've done in creating the graph on the left is we took the value from each peak in the previous graph and then converted it into this graph that you see here. This allows us to see the drop or the sag in the overhead cable as we position the radar sensor from 0 through to 220 metres. We've then converted the bin numbers into the range for the radar, so it's more easily understood. A summary of findings and future work. This article provides a solution to mitigate challenges for inspection and maintenance of overhead transmission lines. The solution minimises engineers working at height and can operate irrespective of dynamic weather conditions. The results display a detection of 4 cables within a single scan and an accuracy of 95.5% when compared to the data collected from the laser rangefinder. This data is reflected in the table in the bottom left. Our future work includes gathering more information from these pylons. We have tested them, as you can see, in very cold weather conditions to identify if there's any line sag or even the tightening of the lines due to these weather conditions. I'd like to thank you all for listening to this presentation and welcome any of you to connect with me via LinkedIn or the Smart Systems Group University of Glasgow YouTube page, where you can find out more on our work. This work that's presented in the bottom left is a symbiotic multi-robot fleet, which is our current work in robotics. On the right hand side I've included one of our references, the symbiotic systems of systems design, and on the bottom right I've included machine learning analysis of non-destructive evaluation data from the FMCW Radar when we were inspecting a wind turbine blade samples. On the top right there I've included our @RobotMyths TikTok page, which is to help anyone who might not have the opportunity to see robotics or see different sensors, and can hopefully inspire them to take a role in engineering. Thank you all very much.